All right, today we're putting on our detective hats. We're going to follow the clues inside a real research paper to investigate a molecule of interest. Our mission? To figure out if this one particular suspect really has what it takes to be a cancer killer. Let's get right into it. First off, let's talk about the stakes of our case. According to the World Health Organization, 2.1 million. That's how many women are diagnosed with breast cancer every single year. The need to find new, better treatments is it's incredibly urgent. This number is exactly why this hunt is so critical. So where do scientists even begin to find a new weapon for this fight? Well, it's a super careful process, a real investigation where every single new molecule is a potential lead. And today, we're going to follow one of those leads, all the way from the lab bench to the final verdict. Okay, so our case is centered on a family of chemical compounds called quinazolines. Now, this particular family, they've got a pretty good track record. Different versions have shown they can work against all sorts of diseases, from malaria to different cancers. So it's a really good place to start looking. And this is our prime suspect. From that big, promising family, researchers created this specific molecule right here, and they called it Compound 6. So the big question we're trying to answer is pretty simple. Is Compound 6 actually capable of killing breast cancer cells? Now here's what's so cool. Scientists don't just, find these molecules lying around. They have to build them, piece by piece, with incredible precision. They're basically molecular architects. So building Compound 6 was basically a two-step job. First, the team built a base structure, which they called Compound 4. Think of it like the frame of a car. Then, in a second step, they bolted on a new chemical group, changing that core structure to create our final suspect, Compound 6. This is its unique chemical fingerprint. Before they ever get their hands dirty in a real lab, a modern investigation like this begins inside a computer. They use these powerful simulations to run a bunch of virtual tests to see if a molecule is even worth the effort in the real world. It saves a ton of time, money, and resources. The first big virtual test they run is called molecular docking. And the idea behind it is actually pretty brilliant. It's like a key fitting into a lock. There's a specific protein that's vital for a cancer cell's survival. That's our lock. And our drug candidate, Compound 6, is the key. This simulation predicts how well that key might fit into the lock and hopefully disable it. Okay, so take a look here. On the left, that's the computer's guess for how our suspect, Compound 6, snuggles up to the target protein. And on the right, that's a well-known heavy-hitting cancer drug called doxorubicin. At first glance, they look kind of similar, right? They seem to hit some of the same spots, which is a good sign. But, the devil's always in the details. And here are those details. We're looking at the binding energy score. Just think of it like a golf score. The lower the number, the better. The tighter the fit. Compound 6 comes in at negative 6.99. Not too shabby. But the known killer, doxorubicin, scores a negative 8.77. That's a much stronger bond. This is our first real clue that maybe, just maybe, our suspect is a little out of its league. But hey, fitting the lock is only one piece of the puzzle. A potential drug also has to be able to travel through the body to even get to the lock. So this is where we run a kind of virtual background check. It's based on something called Lipinski's Rule of 5, and it checks basic stuff like size and solubility to see if a molecule has a good chance of working as a drug in a person. And this is where the plot thickens. Would you look at that? Compound 6 passes its background check with flying colors. It hits every single mark for what a drug-like molecule should look like. So now we've got this conflicting evidence, right? The computer says it doesn't bind as well as the pro, but it also says it has the perfect profile to work in the body. And that creates this moment of real scientific suspense. The computer simulations have given us some hints, some clues, but they can't give us the final answer. There's only one way to know for sure. It's time to move this investigation out of the virtual world and into a real-world lab. Okay, now we're headed for the main event, the showdown in the lab. This is where our suspect, Compound 6, goes head-to-head with actual, living, thriving human breast cancer cells. This is the ultimate test. No more simulations, this is just biological reality. The test they use for this is called the MTT assay, and honestly, the science behind it is just beautiful. You add this yellow chemical to your cells. Now, if the cells are alive and working, their enzymes turn that yellow stuff into a deep purple crystal. So the rule is dead simple. The more purple you see, the more living cancer cells there are. Less purple? That means the cells are dead. First up, let's look at our control group. This is what you get when you just let the breast cancer cells do their thing. See that? It's a deep, rich purple. This is our starting point, our baseline. This is what a healthy, happy colony of cancer cells looks like. All right, moment of truth. Here's the dish where they added compound 6 to the cancer cells. And, well, the picture speaks for itself, doesn't it? It is just as purple as the control. The visual evidence here is pretty clear. Compound 6 didn't really do much of anything. The cancer cells are still very much alive. Now, just to be sure, let's see what a real killer looks like in this test. This is the dish they treated with doxorubicin, and wow, the difference is like night and day. There is almost no purple left at all, meaning the huge majority of cancer cells have been wiped out. This shows you perfectly the difference between an inactive molecule and a potent drug. So the visuals from the lab are pretty damning. The case for compound 6 being a cancer killer is, well, it's falling apart. But in science, you always back up what you see with hard numbers. So it's time for the final verdict. The number that really matters here is called the IC50 value. It's just the concentration of the drug you need to kill half the cells. And again, lower is better. The pro, doxorubicin, has an IC50 of just 0.02. And compound 6? Its value is over 1,000. That's not even in the same ballpark. The data is crystal clear. It's officially classified as non-cytotoxic, which is just a fancy way of saying it doesn't harm the cells.
So the verdict is in. Compound 6 is not the cancer killer we were hoping for. Our suspect is officially not guilty of being an effective anti-cancer drug. For this specific molecule, the case is closed. But in the bigger picture of scientific discovery, this is nowhere near the end of the story.
Now, you might be thinking, well, that was a waste of time. But in science, a result like this is not a failure. It's just data. And it's an incredibly important piece of a much bigger puzzle. Knowing what doesn't work is often just as important as knowing what does. And you don't have to take my word for it. The researchers who did all this work, they said it best themselves. They concluded that this investigation, by ruling out one suspect, has actually paved the way for the discovery of promising next-generation drugs. They've helped narrow the search, and they've given vital clues to the next team of detectives. See, every dead end, every suspect that gets ruled out, it just makes the search smarter. It pushes science forward, pointing the next team down a more promising road. So this isn't really a story about one failed molecule. It's the story of one crucial step in this relentless, hopeful, ongoing investigation to find a cure. Which really just leaves one question. What clue will they follow next?